oral session, we have Yitao Sun from Aalto University speaking about self-consistent tensor network methods for super-moiré matter beyond 1 billion sites. I'm looking forward to it. Please.
Hi everyone, my name is Yitao Sun and I'm from Aalto University, and I'm very honored to be here talking about this research as a first-year PhD student. But also I think I'm in a very interesting situation now, is that my dear supervisor, Aalto, talked about quite something about this work, and spoiler alert, the results figures will basically be the same. I mean, yeah. So, yeah, but anyway, today's talk, I want to make it like, first, I want to make it easier to accept for people who is not very familiar with this tight binding physics. And second is that I would like to provide more technical details about how exactly we constructed those MPUs for the tight binding systems. So let's begin. So basically, for the talk, of course, first talk about background motivation, and then I will first talk about how exactly we can tensorize those tight binding Hamiltonians as MPUs, and then it move on to this mean field algorithm we develop, and eventually we talk about this result and summary you might have seen before. But let's begin. So first of all, what is actually a moiré material? So if you look at this on the left, it's just a very common, honeycomb lattice graphene that is nothing special. But if you have two layers of it, and if you twist a small angle for one of those two layers, you will see this. Maybe it's better to this. You will see this big hexagonal pattern showing. So that is the so-called moiré pattern existing in a material, and that's why we call it moiré materials. But this seems to be something that is pretty trivial. So, I have two layers of materials, I twist it, and that's it, kind of like Oreo. But actually, in labs, there are many experimental works that is very exciting, going all along the way in the past, I say 6-7 years. So, for example, the first one is about so-called magic angle twisted angle parallelographene. Is that for this graphene 1 and graphene 2, if you have this twist angle of exactly at 1.1 degree, you actually have this unconventional superconductivity existing in your bilayer graphene. There's work about this kind of more like exciting about that is something relating to the optical excitations of a material. And they show that actually by changing this twist angle, you're changing this moiré pattern, you can actually control this kind of light excitations from the material. And eventually, this is the very latest one, but also very important. They found this so-called fractional Chern insulator in a twist angle bilayer, this TMD. So this is very, let's say, mind-blowing, because Chern insulator is something that is insulating the book, but as is conducting channels at the edges. But this fractional Chern insulator is kind of like, so you see this, what they measure is kind of like this electrons or this quasi-particles that is conducting actually has this electric charge of a fractional instead of an integer number of electron charge. So it's kind of a new phase of matter existing in such systems. So it's pretty exciting. But in order to describe such systems, or let's just say most material systems we care about, we have this formalism called this tight binding Hamiltonian to describe a system. So it's very simple. Consider a one-dimensional chain, or it could be extended to any kind of two-dimensional lattices. You can think of, okay, it's a chain of this size, this black circles, and the electrons can move freely in this chain. It's hopping, can have interaction with each other. That is interaction, and you can put certain potential or chemical potential or electric field over them to let them feel such on-site potential. And eventually, you can write a Hamiltonian that is like this, including all this hopping, interaction, potential terms. And this C is rather just create a electron at what side, and then annihilate that electron at what side. And this is merely this number, or let's say density of electrons at each side for this operator N. So, but on the more mathematical way of this kind of Hamiltonian is rather just matrices. So in order to actually describe tight binding to describe a system with this kind of tight binding Hamiltonian, it really depends on the unit cell of material. So, for example, if it is for the graphene, you can say, okay, I can use like it's only 2 atoms in a unit cell. I'll say, okay, it's good enough to describe the electronic structure of it. But for this kind of modular systems, you see that now this kind of periodicity of this system exists at this really large modular unit cell that could easily exceed 10,000 atoms in a unit cell. That's exactly for this kind of magic angle magic angle to bilayer graphene. Yeah.
In a typical experimental setup, how many unit cells in the seed? So this is a unit cell, right?
Yeah, sure.
How many unit cells in experimental setup?
First of all, I'm not an experimentalist, but yeah, I mean, it's many thousand indeed.
Many thousands.
Yeah, it's good. Yeah. Yeah, but okay, thank you. But like my supervisor said yesterday, if we have this modular patterns, combined together, so we can create this kind of modular pattern existing in a very large system. It is very interesting, physical phenomena will happen in such systems, but the price we have to pay to actually calculate the electronic structure or simulate it is that now we have to, if before we have like say 10,000 atoms in a unit cell, now we will have a square of 10,000 atoms in a unit cell. So that's basically kind of like a Hamiltonian with size of almost 1 billion times 1 billion. So this is a long-term question for people doing this kind of material simulation, and people have been developing different methods, like what they can do in momentum space, what they can do to actually, for this high performance computation to actually do this kind of calculations. There are many different researchers. But it comes to a question for us is like, okay, this is a very, very large Hamiltonian as a matrix. So, but there's this tensor network method is also used to treat this kind of Hamiltonian of many-body system. Okay, I know that everyone here is very familiar with it. So I would just want to remind you that it's kind of MPS, MPU, and all of this related to all this fantastic many-body physics. But in the end, MPS is a state that has two. If you have an L site MPS, it is rather just represent a state with 2 to the L elements. If it is MPU with L set, it just represents a matrix with a shape of 2 to the L times 2 to the L. So it comes to this final question I have. Is like, so great. We know that this kind of tensor network formalism is very nice for this kind of dimension reduction for this very large matrices and also vectors. And if you think about let's say 8-side spinless fermionic chain, usually you describe it with 8 times 8 Hamiltonian and with a state like 1 times 8 vector. But you can think that, okay, that can actually be encoded into a L-side MPS, 3-side MPS, or a 3-side MPO for describing the system. So we previously called it pseudo-spin basis, but indeed it's more relating to the idea of quantics. So you can think it's this quantics idea. But it is good. It's very good. But how do we actually can achieve this? So that's what I'm going to talk about in the following section of this talk. So the first thing is that it always starts with this one-dimensional nearest neighbor hoping that actually has this matrix form of this one on this first off a diagonal line. And to have a MPU form of that matrix, it is very simple. And you just need to have this tensor product based on this sigma plus and sigma minus and the summation. So you have this MPU exactly stores this matrix. This should be very familiar for people here doing PDE with quantics because it's exactly the Laplacian operator in a one-dimensional system without the diagonal term. And also, I'm only talking about the upper half of this Hamiltonian, but everyone here knows what the actual Hamiltonian should be Hermitian. So, but the Hermitian part of it is rather just on this one line lower than this diagonal line. So I'm just going to talk about half of it. The other is just rather Hermitian conjugate. Anyway, okay, you can do one-dimensional. Okay.
So this has number of terms which is proportional to the size, right?
Yeah.
But the
So-
actual NPO is rank 3 in 1D.
What do you
It looks like it's too big. It's correct, but it's compressible.
what do you mean?
This expression
Yeah.
has a number of terms which is equal to the number of sides.
Yeah.
So if you look at it naively, it's a rank, maximum rank is the number of sides. But the actual rank is rank 3 for
Yeah.
2. So this is the last part of the story, right?
Yeah, I'm not 100% sure I understand the question, but
The whole expression here is a bit confusing
it's a,
because we have L and M inside, but I is a summation. And
okay.
people may read different things from this formula. So maybe if you just tell us what is the bond dimensions.
The bond dimension is
of
it should be like 2 or 3. It's very low. There's a miss of this notion here. There should be something like it's Laplacian, like it's like so sigma plus and then all sigma minus, and then the next one is like sigma plus sigma minus, but before it's like identity. This kind of.
But this is not in NPO form.
No, I mean it's a form of this kind of product of a polymatrices, but you can make it MPO on this. But, yeah. Okay. So basically it's based on. So basically you can think of this tensor products at tensor operator at each side of L set operator, and make it L set MPO out of this kind of stuff. So if it's okay, anyway. Okay. Now this is you could actually make a MPU storing this this matrix with that formula, but this is something very trivial. One-dimensional nearness never hopping. But of course, in modular materials, since will be way more complicated, that the hopping amplitude will be varying over the spatial coordinates. And in order to do that, yes, we applied the quantum cross interpolation for that. I don't need to expand much of it, but so on the very first idea is actually could be that you can actually encode this hopping amplitudes. Suppose they are a function of spatial coordinates, you can actually encode them one by hand. But of course, that will be like a nightmare of time consumption. And that is exactly why we use QTCI for that building of that MPU, because it could just based on this few pivots evaluated, it could give you this MPS storing all this kind of hopping amplitudes across the whole space. And thanks to this kind of modular structures for their hopping amplitudes, they are mostly could be written in a way of function, a function of cosine and sine, and with a good structure. And then we can actually start to build this MPO with this spatially varying hopping amplitudes for this modular systems. So the first thing, so eventually we want to have something like that. And the first thing we do is that, okay, that's the hopping amplitudes as a function of space coordinate. You can use a QTCL with to get this MPS storing all this hopping amplitudes. And the second thing you can do is that based on this MPS, you can actually make an MPU that actually stores this matrix whose diagonal elements are exactly those values stored in that MPS that you interpolated. And the third thing you do is just a simple tensor contraction between this diagonal MPU and this previous first neighbor hopping MPU. And then you can actually probably cast this hopping amplitudes to this first off diagonal line here to realizing this spatially varying hopping amplitudes in the matrix. Yeah.
Sorry, can you just tell us what the legs of the tensor now is? I mean, because you had the site before, now you decompose as a function of x, in quantics? So how many legs?
So we always consider the type binding system with 2 to the L sites. And this legs, if you ask me what is the physical meaning of all these legs, I mean, what do you mean by quantics form on top?
So I think what it's doing is enumerating these 2 to the L sites index, and that index is represented in quantics.
Yeah.
So each of those legs is just one of the levels of the
quantics. So I personally, I would not think this legs for this kind of tight binding system Hamiltonians bear any physical meanings. Rather, they are just rather set of indices and storing those matrices, and allows us to do multiplication of matrices by this kind of tensor contractions. But eventually, through this, you can create this MPO bearing this spatially varying hopping amplitudes for your Moiré system. And well, it's basically the same for the potential term. Assume you have this spatially varying potential term in your Hamiltonian, but this is even more simpler, because this potential terms are rather just on-site terms. So at this step of building a diagonal MPU, you can just say, okay, if this electron density, particle density of my system is a function of spatial coordinates, we can just build a diagonal MPU storing all these densities, and then build this MPU for this potential of the system. Or if the potential is spatially varying, you can also do the same. So, but for all of this before, we are always talking about one-dimensional type binding systems. But of course, all these interesting systems, they live in a two-dimensional world. And in order to build this MPU for the two-dimensional system, a very general approach we have is rather just folding this two-dimensional system. For example, here it's an example of square lattice to a one-dimensional chain. That is, so the order is kind of like the first row and the second row and third row, like that. And this formalism we have already used, it could be easily applied to most two-dimensional lattices you can think of, like triangular lattice, honeycomb, Lieb, Kagome, whatever. And in order to do this, you can see that I'm putting this square lattice as an example. And in order to do this, you see that there are two elements existing for this hopping terms in this system. So one is before the hoppings in the rows. Now it's kind of like, I call it this kind of intra-chain hopping, because now it's a kind of like one-dimensional chain. So I call it one intra-chain hopping, but with breaks in the middle. That is exactly when you change from the first row to second row, or second row to third row. And for building MPU for this, it's rather simple. You can just use how we build this one-dimensional nearest neighbor hopping MPU with just a break in the middle when there's when you reach this length of a row. But for this interchain hopping, that is previously this kind of hoppings in y direction in this order, it's kind of like a little bit hard to build, because you see that now they are kind of become this kind of long range hoppings. Especially we are thinking about the system size with, for example, over 1 billion size, and should be the exponential of 2. So if you think we have a 2 to the 30 size in a square lattice, so it is like 2 to the 15 times 2 to the 15, then this kind of hopping should go through 2 to the 15 size around that. So that would be like very large and long range hopping. So it seems to be hard to build, but actually it's not that hard to build. Again, it's the previous one about how we build this MPU for spatially varying hopping amplitudes. But no, we are kind of thinking this operator, we call it as shifting operator. So why we call it like that is because if you see that by this kind of contraction, you are exactly moving that elements on the diagonal line, one line up to this first off diagonal line. And if you think about the square of this operator, you will see that this can actually help you shift these elements 2 lines up, and the square of that can actually shift elements 4 lines up, so that by doing this, you can actually have this shifting operators that could actually help you shift elements exponentially large. For example, if you say, okay, I want to shift since 2 to the 15 lines up, you can just do this like 3-4 times of this kind of iterations. You will have this operator you need to create such hopping MPU. Yeah.
Boundary condition.
Boundary open, but
Open.
we were always thinking about open, but you can also use closed boundary conditions, because for type-bending Hamiltonians, closed boundary conditions rather just okay, it's a big matrix and there's something right there. We always use open, but we can use periodic. Yeah. So yeah, that is how we all the ingredients we use to build this MPU for a large two-dimensional type-bending Hamiltonian. But if you think about this picture I showed before, you see that, okay, now you know how to build the Hopkins, you know how to build on-site terms, but the interaction term is something that is left unanswered. Of course, it's a hard part of condensed matter physics, and the way we choose to treat such system, such term, is to use mean field algorithm. And the general idea of mean field calculation is simple. So you have this Hamiltonian, you have this single particle term that is easy to treat, and this two-body or even many-body terms that is hard to treat. And the mean field treatment is that for this many-body term, you just focus on one of them and using all other stuff as the background potential field applying on that term you focus on, and you choose this single term you want to focus on, and do the summation of all these kind of single terms existing in the system, and then you have this mean field Hamiltonian that is single body and allows you to write stuff in as a single body Hamiltonian, and the iterations of mean field calculation is just like that. So eventually we want to solve the system. We want to get the proper Hamiltonian that could describe the system, and also we are caring about these correlators we want to look at. So with its initial guess of this mean field, we can build this mean field Hamiltonian and solve these Hamiltonians for these correlators. And with these correlators, they are used as new mean field to update the mean field Hamiltonian for next round of iteration. Eventually, we do this iteration until it converges based on this difference of these correlators in each iteration. And in our case, we are using this Hubbard model and at this half-filling situation where you see that now this two-body term here that is about this electron density of spin-up electron densities times the spin-down electron densities. And the mean field treatment is that we consider only one type of spin for this Hamiltonian, and consider the other one as a background field, as chi. And then with this initial guess of chi, we can build this mean field Hamiltonian for both spin-up and spin-down electrons, and we solve it. And we update this this mean field during each loop, and eventually for this till it converged. And this criteria for the convergence is rather just the difference between the the electron density of this round of iteration and the previous round of iteration with this epsilon. Now, in order to actually get this expectation values of electron densities, we apply this kernel polynomial method, where this very general definition of KPM, and you see that with a function defined on this -1 to 1, you can actually use this Chebyshev polynomial to expand it. This is big Tnx and has that form, and it's also based on this Chebyshev moments, which can be calculated using this integral. It's pretty general, but in our case, in order to get the electron densities, we first need to get the local densities of the system at different energies and sites of the system. That is exactly with that formula, and we use KPM to open this to expand this delta function and have this big formula. But now, please pay attention that there is two types of there's Chebyshev polynomials for two stuff. The first thing is for this mean field Hamiltonian, and the second thing is Chebyshev polynomial for the energy. So for the energies, they are rather just simple. They're just with this explicit form. And to get the electron densities, you just do this integral over this energy, and you see that this could be integrated to this, and it's gone. But this still remains about this Chebyshev polynomials of this mean-field Hamiltonians. Now this seems to be hard to do, but one good thing about the network is that you can, freely, at the most times, freely contract and do summations between each other. But in order to have this polynomials of Chebyshev polynomials of the Hamiltonians, we need to use this Chebyshev recursion relation. That the zeroth order of Chebyshev polynomial is identity. The first one is just this Hamiltonian, and from the second one, it follows this relation. And in our case, well, we can just have everything as MPUs. For the zeroth order, it's just identity MPU. For the first order, we have this Hamiltonian MPU. You know how to build it. And for this following rounds of this KPM expansion, you can just always do this 2 times this contraction minus this MPU that following this recursion relation. So it's easy to get all of these Chebyshev polynomials as MPUs. And now we have basically everything, but still, eventually you have the electron density is something like 1 minus this big chunk of MPS, MPU, MPS contraction. I call it this big chunk as a MPU of A, and it's like red squares. And you can think not this electron densities, rather this stuff. Well, this yellow MPUs are like the state vector or MPS for referring to this site of I of the system. But now you think about it. If we have, again, a system size over 1 billion, but should we need to go over every site of the system in order to get this electron densities across the system? The answer is no, because we can actually view this MPS, MPU, MPS contraction as a function of I and actually give it to QDCI and then let it help us to actually interpolate the electron densities across the system. With that, we can, again, build this diagonal MPU and then use that diagonal MPU to update the mean field Hamiltonian for next round of calculation. And for this, it works actually very, very well for all this stuff we've been doing. Basically, this bound dimension of this electron densities is something below 50 or 30 or something, based on the different dimension and the question of your different dimensions and different systems of your lattice of your system. So yeah, that's a big wrap. That is how we perform this mean field calculations for this very large type-binding Hamiltonians. So the first thing we do is to, based on the system, write a MPU of the system that is like LSat MPU, storing all these parameters 2 to the L times 2 to the L Hamiltonian. With that MPU and with this indigo, with this crayon guess of this electron densities, we can build this mean field Hamiltonian. And from this mean field Hamiltonian, we can get this new electron densities of the system. And with that, build this mean field Hamiltonian for next round of calculation. So all of these circles and iterations are based on MPUs and MPS without any metrics including. Eventually, I'll talk about some results and summary of this stuff. So we first did this calculation on a one-dimensional super-moiré system. The Hamiltonian is something like this. So basically, you see that it's very similar to the Hubbard Hamiltonian I showed before, with this hopping amplitudes and these interactions that could be made change over the space. And the system size we choose is 2 to the 30 sites. That is exactly a little bit over 1 billion sites. And that will correspond to this L equals 30 tensor networks across this all calculations. And this criteria we set for this kind of convergence of mean field calculation is 10 to the minus 3. We already consider it's a very good threshold we set for this kind of calculations. And This is the result for a one-dimensional system. And you can see that where it's super-moiré is because of the modulation we apply on these hopping amplitudes. You see that for the first modulation, it's oscillate on the scale of 10 to the 8. And for the second modulation, it's just oscillate on the scale of 1 or 2. And the result, local density of the systems looks like this. So this is the system result interaction, so there's no gap. This is a result with interaction, that is what we really care about. And you can see that for with or without interaction, the shape of this local density state properly follow this modulation we apply, both on this large scale and small scale. And also this gap opening also follows this modulation. And a very surprising thing we first have it is that we actually have these results within around 11, 12 hours. So this is on a single core of a CPU. So this is really exciting because before, I don't think no one can actually achieve something like this for this very large tight binding systems. We did some benchmarkings for this stuff. The first thing we do is that if we fix everything else, just change the size of the system, you can see that the time needed for 10 rounds of mean field calculation actually grows linearly with this system size grows exponentially. So this is kind of common for the tensor network and people that, okay, you do this and you have this exponential or logarithm increase in your computation, that's efficiency. But before, there's people doing mean field. For people doing mean field, the state of the art of their algorithm is something like linear complexity, and with many good ideas of how to accelerate the whole calculation. So, but now with tensor network, you can easily achieve this kind of linear increase in time against this exponential increase in system size. But of course, we cannot easily climb this complexity. I mean, like it could be problem dependent. Of course, we need to do more benchmarking about it. But this is inspiring to see it. And we also did this precision benchmark with the result that's calculated on a system with 10 to the 10 sites with using exact diagonalization. And you can see that with the bound dimension for our approach are going to the 100. The difference between the converged electron densities of our algorithm and exact diagonalization is below 10 to the minus 3. So we consider it's really good, and that's why for all calculations applied for our computation, we always set this bound dimension to 100. Yeah.
The comparison is for the same mean field.
The compression is
Comparison.
Yeah, exactly the same mean field between ED and yeah.
So I'm asking this question because
Thank you. The convergence is not exponential, something like you see some saturations.
Yeah, but
So, do you have any idea?
We think this is due to because I see that I think it's based on the number of Chebyshev polynomials you use, because the more you use, it should be more precise. But for here, it's like we fix the number of Chebyshev polynomials at a rather not very large, I would say, number, just to want to see the difference, the influence of bound dimension over this calculation.
How much? You say number of Chebyshev? You said not big.
Because this one Solon size system, I assume it to be something like 100, around 100, yeah. But yeah, of course, we use more for actual billion size system. But this is like rather just to test what is the influence of bound dimension over this precision. Okay. And then, of course, after we benchmark over one-dimensional systems, how much then? Okay. So we have a few examples of doing calculation over two-dimensional systems. For example, it's super-moiré 8-fold interaction term with this form of modulation, and you actually see this modulation here. Is that all this 8-fold stuff is actually based on many small 8-fold patterns, and we calculate the mean field of it, and we eventually plot the magnetization of the system with just the absolute difference between the spin up electron densities and spin down electron densities at all sides. And you can see that the magnetization actually perfectly follows the modulation, both at the very large scale, this scale, and this very small scale. So we are very happy about it. And we also did something about graphene. That's what people really care about, I think, for two-dimensional system. And it also works pretty nicely. But yeah, eventually, that's basically all of it. I'm just want to say that the thing we did is basically we found a way to encode this super large tight binding Hamiltonians of basically common one-dimensional and two-dimensional systems as MPUs, and use this advantage of MPUs to largely first accelerate the calculations and also enable us to easily do calculation for super large systems. And we, based on that, we developed this mean field algorithm and for the super-moiré systems and did some benchmarks and the results that seems pretty promising. But of course, I think that more efforts should be paid to further, let's say, benchmarking and understanding what is actually what is the meaning of all these parameters we have for this kind of calculations. And eventually, yes, we have other works based on this kind of formalism. We have like 2 or 3 posters about it in the poster session part. So if you are interested, you can take a look and maybe ask about it. I'll be happy to answer them. Thank you.
Thank you very much. Thank you for your talk. I'm sure there are questions in the room.
I have actually a comment on the question.
Yep.
The comment is on the shift operator. So the shift operator for any translation is rank 2, and it can be constructed in a few lines analytically on the blackboard.
You mean like it can only move things like to the something lines?
No, anything you want to move by.
You can move by anything. Because you can like you can express any number by its binary form, right?
But you don't need to do what you, if I understood correctly, you did like MPO contractions.
Yeah.
Yeah, you don't need to do that. You can just write a rank 2 MPO on the blackboard and just put it in your code. It's just 5 lines of, it's really
Okay.
like a straightforward.
Yeah, I mean, okay, thanks.
You don't need this.
Don't need this. Okay, yes.
And the question is, when you do Chebyshev, like you can have like this Gibbs oscillation. So people sometimes put some damping. So did you do something about it?
Yeah, I did not show it, but we use the Jackson kernel to truncate.
Okay.
Yeah.
So let me agree with Xavier. Vladimir Kozeyev did a lot of work on QTT structure of operators like a shift operator and similar operators for PDEs several years ago when he did his PhD in Zurich. So Vladimir Kozeyev, his PhD thesis has a lot of results on QTT structure. Yeah. Vladimir Kozeyev. So he did a PhD with Kozeyev. Yeah. He's now in Vienna.
I mean, like a lot of this.
So yeah, his PhD was about QTT structure
Okay.
of typical operators that appear in partial differential equations, and of course, shift operator is one of them.
Okay.
Yeah, yeah. And this is now probably 10 years ago.
10 years ago.
Yeah,
Okay.
yeah. So
So we are
this results are
reinventing this.
quite well known.
Okay.
Any more questions in the room, please?
Yeah, thank you for a nice talk. So I'm not in this field in the sense that I don't know how big a type binding model people can solve with just ED, because this is not an interactive system.
If it's just ED, I think below 1 million, that's already something very not easy to do. With KPM, you can do something about 1 million. And there are some people, I mean, like as I said, like so this super large tight binding system simulation is actually a field that exists for quite some years. For some years, there are people actually can do over 1 billion size with matrices. There's a package about it. It's called Kite. But the problem of that is that they have, first of all, it took them really quite some year to actually have this package that could actually works nicely. And second thing is that they cannot store anything, so they have to compute everything, on the fly and without storing anything, but just calculate the eventual, for example, tensor state of the system. But for first of all, you can, to realize it, you don't need many lines of code, the first thing. And second thing is that you can actually store everything you want. It's rather just, I don't know, 20, 30, 40 site MPS, MPU, and you can easily extract information from it. Which of course we will need for the improvement of this, of course, but I think that's a very advantage of this approach.
Okay.
Of this stuff.
Thank you for the talk. So could you go back to the page showing the alignment of our X and Y coordinates? Long range hopping.
Yeah, this one. Yeah.
Yeah. So
this one. Okay.
So I wonder, I think you're using I'm trying to connect this to normal interleaved representation or something like that, 2D. So I think you have one block for bits of X and bits for Y.
Right, like this.
Mm-hmm.
So the Hamiltonian is
Each linear dimension is to the power n.
Yeah.
Right.
Yeah.
So I wonder, so if you define bits for X and Y, how's they aligned? I think you're using, you have X bits and Y bits. Right?
We in this way of building it, we do not actually have a clear, let's say, X bits and Y bits. Rather, it's just we just construct the tensor network stuff based on this order we have. And of course, I understand you ask this problem because you can do two-dimensional TCI and you have X bits and Y bits. But for us, we really don't have this clear.
But virtually you have, right? And if you use let me discuss. Sorry.
Yeah. I mean, like more. I think it's more about legs actually.
Confuses.
I can. I understand.
Thank you. More questions in the room, please?
Very interesting work. I was just curious, like a simple question about, are you thinking about now using this in methods where you can treat the interactions at a higher level, like, do perturbation theory? Have you thought about, or like, what about time dependence? Have you worked on?
Yeah, I mean, like as for now, we have this formalism to do this. We can think in many directions. For example, for interactions, and now we are doing this on-site interaction. Of course, you can think about what is a 1/r interaction, that is, or long-range interaction.
But I meant, like, what if you go beyond Hartree?
Beyond mean field. Yes, I think we can do that. We are working on a very initial project about performing a RPLA. Random phase approximation with this formalism. So of course it will be harder, but from my perspective, I mean, most things you can do with matrices is, for now, you can do with MPUs. So, but of course, how will the precision of the calculations, how every factor will influence everything, that is definitely requires more benchmarking and this and that. Yeah, but thank you.
Thank you. More questions in the room? I will probably ask one from myself. Can you go to your first picture when you show the geometry of the physics? The very first picture, on the very first slide. Yes.
This one.
So you have atoms here, and they form this beautiful pattern. And then you scale out, and there are more atoms forming the second layer of this beautiful pattern, like even a fractal. It's exciting. But then you choose 10 to 9 atoms for your simulation.
Yeah.
Yeah?
Yeah.
Which one do you choose?
One third.
So you just draw a circle, and just whatever
first of all,
the
calculation we did perform, we showed you is not about this. It's not exactly this system. Rather, we just show we can do this system up to this level of number of atoms in a unit cell. But if we really want to do it, it will be about all these atoms within this big hexagonal shape.
Okay, and now the question is, what if the number of these atoms is not exactly the power?
It's not the power of 2.
How do you fix this?
First of all, I would say that even if it is not the power of 2, we can somehow do it. It's just that we need to use the MPU that has more elements than this number of atoms in that. And second thing is that let's think about for a super-moiré system that has so many atoms in there. You really want to have an explicit number of that atoms in a unit cell you really want to simulate. Or I would just think it's actually at the same level of quantity that is already enough. That's
Okay, so
for this is my perspective.
I guess the answer is that the choice is rather arbitrary and not important, right?
Yeah, I mean,
Okay.
at least from my side, at this number of atoms in the unit cell, you just at the same level number of quantity should be fine.
Thank you very much.
No problem.
So just a physics question. I believe in these Moiré systems, one issue is that the structure actually reconstructs. If you put two perfect lattices on top of each other and you change them a little bit, the atoms want to rearrange. And it's a question in computational physics to compute this reconstruction,
Yeah, I mean,
which
like,
would need a different type of model approach. But
yeah, I mean,
do you see any perspectives for tackling that type of question using these methods?
first of all, are you suggesting about this kind of lattice relaxation?
Yes, exactly.
So first of all, usually people do that with DFT, I guess. But for our
Well, you need different methods, but you still have to
a large,
encode
very
a
large.
huge number of
Yeah.
sites.
Yeah, first of all, I am not the expert of that. I don't quite
I realize
understand
this,
the
yeah.
algorithm of how they actually calculate the relaxed lattice. But yeah, maybe we can think about them later. I'm not very sure about it.
Thank you very much. It's surely a very exciting and novel approach to this well-known problem. So yeah, a lot of questions can be asked. Are there any more questions in the room? And if not, let's thank the speaker again.